Hello everyone. In this video, I am going to explain you about topic sampling. Now let us start the class. Firstly, we will see about the introduction of the sampling. Sampling is a process of converting a continuous time signal into discrete time signal. Now already we learned about continuous time signal and discrete time signal. Now by using this sampling process, we are converting the continuous time signal into a discrete time signal. Now this is the figure showing regarding sampling process. Here we are considering a continuous time signal x of t, and this x of t is multiplying with the periodic impulse train, and it is denoting with delta t of t. And when we are multiplying both these signals, we are going to get x of nt equal to x of n, that is nothing but discrete time signal. We are denoting with x of n. Now here, after this sampling process, we are going to obtain the signal is defined at discrete instance of time, and the time interval between two subsequent sampling instance is called sampling interval. Now here, if we observe this sampling process figure, the continuous time domain signal same will be shown here. But this figure is showing here in discrete time domain. That means this discrete time signal is going to define a discrete instance of time. Now here, this n will be the integer numbers like 0, plus or minus 1, plus or minus 2, and so on. And this capital T will be showing that sampling interval. For example, if we consider the samples here, in between these two samples, whatever the time is showing here, that will be the sampling interval, nothing but capital T. And by using this sampling interval, we are going to find the sampling frequency, that is denoting with as Fs, will be equal to 1 divided by T. Now, here, signal sampling rate must be kept sufficiently high so that the original signal can be reconstructed from its samples. Now I will explain this point by considering one example. Like here, x of t is a continuous time domain sinusoidal signal. If we multiply this signal with a periodic impulse train, that is means we are going to do the sampling process. And after that, if we obtain a discrete time domain signal x of nt like this, if we see this figure, the time interval between two samples is very much more than comparing with this signal. So, when capital T is more means the sampling frequency is going to be very less. So, when this time interval in between two successive samples is more means we cannot draw the continuous time domain signal original as it is. So here we cannot say that this is a sinusoidal signal because the time period between two samples is more. So from this sampling process, the one point we need to consider is that the time interval between two samples is must going to be less and the sampling frequency must be more. Now we will see the another way of representing the discrete time domain signal, nothing but sampled signal xs of t, and it will be equal to x of t multiplied by delta t of t, where here this x of t will be equal to continuous time domain sinusoidal signal and this delta t of t will be the periodic impulse train signal, where this delta t of t can be expressed as sum of n equal to minus infinity to plus infinity delta of t minus nt. Now if we substitute this equation 1 in equation 2, we may get the mathematical expression regarding sampled signal xs of t will be like this. Now applying Fourier transform on both the sides to this expression 3, now we will get the Fourier transform of xs of t is given by xs of j omega will be equal to 1 by t sum of m equal to minus infinity to plus infinity x of j of omega minus 2 pi m divided by t here. Now by applying Fourier transform, we are converting time domain signal into frequency domain signal. Now, if we observe this expression, the Fourier transform of sampled signal is given by infinite sum of shifted replicas of the Fourier transform of the original signal. Now here, let us consider the signal x of t is band limited to fm, that is the highest frequency component of x of t is fm. Then here x of j omega will be equal to 0 for omega values are greater than omega m, where omega m will be equal to 2 pi fm. If we observe the waveforms here, now this will be the frequency spectrum of continuous time domain signal x of t. Now here this is the waveform representing when the frequency spectrum when pi by t will be equal to omega m, and this waveform is going to represent the frequency spectrum of continuous time domain signal where pi by t is greater than omega m. Now this waveform is going to represent pi by t is less than omega m. Now by considering one example, let us understand about the frequency aliasing. Now let us consider a point omega 1 which falls in the region of overlap. Now here we considered omega 1 point in this overlap period. The frequency spectrum at omega equal to omega 1 is the sum of two components. One component is excess of j omega 1 and the other component is excess of j of 2 pi by t minus omega 1. This high frequency component 2 pi by t minus omega 1 is folded in about the folding frequency pi by t and appears as low frequency at omega 1. This superimposition of high frequency component on the low frequency is known as frequency aliasing. Because of aliasing, the spectrum x of j omega is no longer recoverable from the spectrum excess of j omega. From the figure here, we can note that aliasing error can be prevented if the highest frequency component omega m in the signal x of t is less than or equal to pi by t. That is, pi by t must be greater than or equal to omega m. So by considering these two waveforms, we can reconstruct the original signal given continuous time domain signal. Now by considering this pi by t is less than omega m means we cannot reconstruct the given continuous time domain signal. Now by considering the condition pi by t greater than or equal to omega m, we can find that fs is greater than or equal to 2 fm. Means here fs will be the sampling frequency, fm will be the maximum frequency. So here to avoid aliasing, the sampling frequency must be greater than twice the highest frequency present in the signal. Now we will see the definitions of sampling theorem and Nyquist rate. Here the sampling theorem states that a band limited signal x of t with x of j omega equal to 0 for omega values greater than omega m can be uniquely determined from its samples x of nt if the sampling frequency fs is greater than or equal to 2 fm, that is, sampling frequency must be at least twice the highest frequency present in the signal. Now coming to the Nyquist rate, the minimum rate at which a signal can be sampled and still be reconstructed from its samples is called Nyquist rate. It is always equal to 2 fm. The Nyquist rate shows that fs will be equal to 2 fm.